Assalamualaikum and hello to everyone. In this video lesson, we will continue with our syllabus for Chapter 3. In this video lesson, we will cover the final subtopic for Chapter 3. Since this subtopic is quite long, it will be divided into two parts. And on the right of the screen, written in red, are the objectives for this subtopic. Before we look at how to develop the isentropic efficiencies for steady flow devices, it is best if we know the definition for isentropic efficiency. As we can read on the left, isentropic efficiency is the parameter to measure the degree of degradation of energy in steady flow devices. Degradation here means the loss in energy quality, as mentioned in the second law of thermodynamics, which states that energy flows in the direction of decreasing quality. In terms of performance, if a steady flow device has a high isentropic efficiency, it means that less energy is lost and more power output can be achieved. However, for any steady flow devices, the isentropic efficiency cannot be higher than 100%. For actual steady flow devices, the isentropic efficiencies are normally between 0 and 100% or in a ratio 0 to 1. In this subtopic, we will look at how to develop and apply the isentropic efficiencies for three steady flow devices, which are turbines, compressors, and nozzles. Now, let's us look at the first isentropic efficiency, which is for turbines. Now, we know that turbines are work-producing devices. The higher amount of work output, the better the performance of a turbine. Unfortunately, for turbines, actual work output is less than the ideal work output. Therefore, in terms of isentropic efficiency for a turbine can be written as follows. The term for work output in the equation W dot out is obtained from using the steady flow energy equation. Okay, now let's look at the first example for turbines on how to apply the isentropic efficiency equation. You can pause the video to read and understand the question properly. Now, before we proceed with step 1, it must be highlighted since the question involves the isentropic efficiency for steady flow devices. All items asked in the question must be based on actual conditions. For example, the exit temperature for item number 1 is the actual exit temperature. And for item number 2, the shaft power output here is the actual shaft power output. Now, for step 1, please try to draw the schematic diagram for a turbine and do not forget to label the amount of heat loss, which is 7% of the work output. For step 2, since the substance is a gas, to find the actual exit temperature at state 2, we will use the SFEE, and please remember to write the conditions given in the question. Start with writing the general equation for SFEE and cancel the terms based on the conditions given. Then write what is left and remember to replace Q out with the information provided in the question. Rearrange the equation to find for work output. Now, since the substance is a gas, H is replaced with CPT. But remember that this is only the general equation for work output. This equation must be rewritten to take into consideration the ideal and actual conditions. Now, for ideal conditions, the subscript S is written at workout and T2. For actual conditions, the subscript A is written at workout and T2. And this equation for actual work output can be used to solve for the exit temperature at state 2. To solve for actual shaft power output, we must first solve for the ideal work output, and then using the isentropic efficiency equation for turbines, we can solve for the actual work output. For step 3, determine the required properties at each state. For state 1, remember to convert the temperature in units Kelvin. For state 2, using the isentropic relationship equation, we can calculate for the ideal temperature at state 2 T2S. In step 4, to solve for this question, we must first calculate the ideal work output. Substituting the required values, we can see here the ideal work output equals to 1880.09 kilowatts. Now, using the isentropic efficiency equation, we can solve for actual work output, which we can see here equals to 1598.07 kilowatts. To solve for actual temperature at state 2, T2A, we will use the actual work output equation, and substituting the required values, we can solve for actual exit temperature at state 2, which we can see here equals to 821.79 kelvins. But don't forget to convert it into degrees Celsius as mentioned in the question. Now, some might get slightly different answers due to the amount of decimal points taken during the calculation. Now, let's look at the second example involving isentropic efficiency for turbines. You can pause to read and understand the question properly. For step 1, please try to draw the schematic diagram and don't forget to label for actual work output given in the question in units kilowatts. For step 2, to solve for isentropic efficiency, we will use the isentropic efficiency equation for turbines. Now, in this equation, the term for work output is obtained from using the steady flow energy equation, and remember to write the conditions given in the question. Start with writing the general SFEE and then cancel the terms based on the conditions given. Write what is left of the equation and rearrange to find for work output. Remember that this is only the general equation. This equation must be rewritten to take into consideration the ideal and actual conditions. For mass flow rate, since the actual work output is given, we can use the following relationship to find for mass flow rate. For step 3, find the required properties for each state. At state 1, remember to check the phase of the substance before reading the properties. And using the appropriate tables, we will read for specific enthalpy, H1, and specific entropy, S1. The specific entropy is read because it is required at state 2 to find the properties for ideal conditions. At state 2, for the given information, solve for ideal conditions first. For ideal conditions, the specific entropy is the same as state 1. And we can check for the phase, which we can see here state 2 is in the mixture region. Therefore, using the equation of mixture, we must find the quality first, which we can see here equals to 0.897. And using the equation for mixture again, we can solve for the ideal specific enthalpy H2S at state 2, which we can see here equals to 2407.9 kilojoules per kg. Next, we solve for the actual conditions using the given information. Remember to check for the phase again, and using the appropriate table, we can read for actual specific enthalpy H2A at state 2. For step 4, substitute and solve for the isentropic efficiency, which we can see here equals to 66.7%. And then for mass flow rate, which we can see here equals to 3.64 kilograms per second. We have come to the end of this video lesson. We will continue with the remaining isentropic efficiencies in the next video lesson. If there are any questions regarding this video lesson, please do leave a comment at the forum section. Thank you for your attention and have a good day.